Okay, this chapter 2 is Introduction to Microcontrollers. So we're going to look at the difference between a microprocessor-based system and a microcontroller, and then what's inside a microcontroller in a hardware viewpoint, and understand that better, and also the registers, program memories in a microcontroller, and then we move on to the next chapter for programming. Okay, so let's So microprocessor is a CPU. So here in this diagram you can see CPU, and it's a one single chip, and it is connected to ROM, which has program, random access memory, I/O port, timers, peripherals by a single system bus. But they're all external to microprocessor. So it's like if you want to build this, you need a one single board having that one separately. So microprocessor chip and all the others are connected. So you will find that microprocessor cannot work on its own without this. We know that. Without that, microprocessor central processing unit, that's all it is. And it needs to be connected to this externally. And application of microprocessor include desktop PCs. You look at desktop PC and there's a board there, microprocessor there, lots of RAMs, lots of ROMs, lots of input-output peripherals. Laptops, tablets uses this technology. And I'll give you a reason in a minute. Then you look at a microcontroller, all these are embedded in one chip. That's microcontroller. So you will find it's a small dedicated computer on a single chip containing the microprocessor inside, memory inside, and programmable input-output. And if you look at here, this is a microcontroller IC, one single chip. It has got microprocessor inside, data memory, program memory, counters, peripherals, input-output, analog input-output, all in one. You can give external clock or you can use internal clock as well. That's all inside. As soon as you put inside everything, then your overall operation, frequency of operation will go down. The clock frequency, you cannot have very high clock frequencies. You will find most of the microcontroller operate at 40 megahertz, below 40 megahertz. As soon as you have items separately outside and connect them, they can operate a higher frequency. So microprocessor-based system can operate at about 1 gigahertz. So that's the advantage. So you got to make a choice. What is this application? Is an application requires high speed or lower speed, medium speed, then you may end up with a microcontroller. It's a lot faster, a lot easier to implement. One single chip and small connections. You want a laptop, you want to build a laptop and it needs to do a lot of things a lot faster, then you got to go for a microprocessor outside, everything outside, and in a board you need to build that. Okay? So that's the difference between single chip against multiple chip connected externally. The microcontroller that you're going to learn in this course is called PIC microcontroller. PIC stands for Programmable Interface Controller. That's the PIC microcontroller. So PIC microcontrollers are designed by microchip technology. You can go onto the web and Google through microchip technology, and there are varieties of microcontrollers available. So I've selected some of them. Some of them are 8-bit microcontroller, right? So it's called 8-bit PIC MCU. MCU stands for microcontroller. DSC stands for digital signal controller. And you have PIC 10, PIC 12, PIC 16, PIC 18. There are many varieties there. We don't need to go through them in detail. We will be choosing the PIC 16. That's what you will be using in the laboratory, right? I'll go within PIC 16. There are various varieties as well. Then a 16-bit microcontroller unit available. Again, these ones are available as well. Depends on the applications that you want to use. 16-bit DSP also, DSP, which is the digital signal controller, also available. And if you are using for music applications, you want a chip which needs to do filtering and processing, then you will choose this particular microcontroller. Then you've got a higher application, you can have PIC 32. So in our course, we will be in this course, we will look at the 8-bit PIC microcontroller, which is PIC16 family, PIC16 family, but it's called PIC16F886. So all the instruction set that you learn is for that particular microcontroller, and you know, is a subset of others as well, you know, or superset of others as well. So this particular microcontroller is what we will be looking at in our course. Let's look at the microcontroller feature in this one actually. It's 28-pin low power CMOS with the flash-based 8-bit microcontroller. The memory is flash memory. The power supply voltage is 2.0 to 5.5 volts. So we can operate at 5 volts normally. Normal IC operates at 5 volts or 3.5 volts. You can use that. 35 single word instruction. So it's called RIC, mean RISC instruction architecture. It's a reduced instruction. R mean reduced, S mean, I mean instruction, reduced instruction set. So you have 35 single word instruction inside. You have to use all of those. That means they are written in binary inside. But we will learn it how to use this instruction set to do a particular task. There are 256 bytes of electrically programmable, erasable and programmable data memory available, which we can use. And this memory can be written more than 1 million times. So you can keep writing and erasing more than 1 million times. Then you've got an 8K flash memory inside, which we look at as well. And then data memory also, you've got 368 bytes. And we look at why you have different type of hardware stack, and I'll explain what stack means. 24 input-output pins. So if you look at it, there are 14. It's input-output pins. Beg your pardon. Input-output pins are, you will find there are 1 of them, 2 of them, 3 of them, 4 of them. You can count them, and there will be 24 of them altogether. 11 channels of ATD converter. So if you want to convert analog signal to digital, you've got 11 channels. You've got a comparators as well. And there are comparators available. And then you've got external communication. You can have serial communications, and it's available to you. Clock speed, you can go up to 20 megahertz. And then you've got internal oscillators also available for you. They are software selectable oscillators internally. You can select them from that frequency to that. So the pin diagram, you can see here pin diagram of this microcontroller. It's got all sort of function. One pin can do 2 functions. Now in this case, one pin can do 1, 2, 3, 4 functions. So you need to select which function you're going to do, and we will learn that how to do it. So pin description, so describing the pin, each pin, there are 28 pins there, and we are describing each pin. Each pin would have functions here. So if you take that one, pin 1, I won't go through every one of them. It's a RE3 mean it's an input port E, and MCLR bar means low level for resetting. If you want to reset the microcontroller, you put a 0 to that particular line, and then VPP means programming voltage. You know what voltage you want to connect, programming voltage that you need. You can connect that there. So the way it is that it has got 3 functions, and you select one by default. Other one you need to program it. Similarly, there are other pins 2, 3, 4, and I won't go through them in detail. I just want to give you so that you can refer them later on. AN stands for analog input output, TTL stands for TTL compatible, and CMOS stands for CMOS compatible input output. So it depends on where you are going to connect to externally. You need to look at the compatibility and select the ports accordingly, and which we will teach you how to do it. But for the moment, you need to know what these pins are. You don't need to remember any of these pins. You will give this data sheet. So again, if you go through further on this pin, so if I just pick up another pin, pin 11, Pin 11 has got a input-output port C. You can use it as an input-output, or it can be used as timer 1 oscillator output if you want to look at the oscillator output of a timer 1, or timer 1 clock input. You can use an input clock. So how do you use one of them? You're going to select them accordingly, and how selection is a selection procedure which we will write in. We need to control a bit inside the microcontroller to do that. We'll come back to that. And so again, this is something you look up whenever you want it. You don't remember anything here. Now look at the block diagram of the microcontroller. So I've just simplified the block diagram in a form that a microcontroller has got a CPU with its 35 instruction. It can only understand the 35 machine codes. Instruction it will, if you have it can't understand more than that. And everything needs to be done within that. And then you will find special function registers. That's here in the data memory. Particular registers are allocated for certain things. And then you have got general purpose registers. That's also in the data memory. So this is the data memory of 368. It has got all these registers. And you may ask a question, how do you access these registers? We'll come back to that. Then you have got the serial communication block. It has got. And then you've got, in the serial communication, you've got these two communication process. How do you do that? And then you've got ATD converter. Then you've got a comparators, pulse width modulation. Then you've got ports, port A, port B, port C, port E. You can program them as input or output ports. Some are input port only, some are programmable input output port. Then you can have a program memory. This is where you store your program, and the microcontroller takes the information from here and to execute. And then electrically erasable program memory you have if you want to save. If you want to save a program, when you turn off the power, you still want to have it when you turn it on later on, so you can use that. And this can be expanded format, and this is not something you want to go through them now, but if I expand this one, you can see port A has got 8-bit, port B has got 8-bit, port C has got 8, and port E only have 1 at the moment. And analog ATD converter, all these are, if you look at all these are the particular pins in your chip. And then you have got the flash memory inside, plus all the timers inside, and all the RAM inside, and the stack inside. And this is the arithmetic logic unit, how it does the calculation is all in a form. For the moment, that block schematic understanding of this particular one, if you understood what it has, then we can then select each function and write program to get the computer to execute. So the first one, I'm going to look at the memory organization inside the computer. How is this organized and what is this? So the microcontroller program memory, I'm only looking at the program memory, right? So you can go back to the diagram and you will see the difference between program memory and data memory, right? So the program memory, every memory must have an address. We looked at it earlier. It has got a 13-bit program counter. So the program counter starts at a particular value. Every time it takes instruction, the counter goes upwards because it needs to point. So this counter is pointing to the memory. The memory itself is divided into sections, page 0, page 1, page 2, page 3. So your program can only reside here. It won't continue from there to there. You need to, if you want program here, then you need to write tell the computer the instruction to go execute from there, or execute from here, or execute from here. You can have program anywhere, but it's not contiguous. If you start from the top, it won't go through all the way through page 0 to page 3. You need to move them around a bit. Yeah. We'll come back to that. And the program memory is not 8-bit, it's a 14-bit there. And you will see later on, 8-bit is the actual data information, and the 6-bit is your instruction, machine code. And then what happened is we have got what we call as a stack. There are 8-level stack. Remember, you would have done subroutines. So when it is doing a main program, you say, oh, I want to go out and do something and come back. So when you go out and come back, where to come back need to be stored. That's what we call stack. And we'll come back in the next slide, I'll explain to you that. So 8-level stack, which is also 13 bits, and program memory is also, that's 14 bits. And the program memory will be 8 bits of data plus 6 bits of instruction. The 35 instruction we told you that they are in terms of 6 bits. Now the program counter. So we go a bit more detail with the program counter. We're going to look at this program counter a bit in bit more detail. Just to give you an understanding. Okay, so the program counter is a 13-bit counter capable of addressing from 0040 to 1FF. That's your space. So it starts from 00, the address, and it ends up as 1FF. That's your program memory. And it has got a data bus, which takes the data out of that. It's a 14-bit data. So the 13-bit counter, minimum value is here and the other one is there. That's what it's addressing. So it's when you address a particular location, so in this case if it's addressing 0800, and the 6-bit opcode means operational code, which is your instruction, and then the 8-bit is the data. It could be, instruction tells you, take this data and put it in a particular location. That may be the instruction. So it will take this data, put it in a location. We'll learn more on that. And during the power up, when you turn on the system, the microcontroller always come to the, set up memory address 0. It will be always pointing to that. Always. So when you are in trouble and you reset the system, the program counter goes upwards and pointing to that. And it's pointing to the 000 location. So its memory address is 0. You need to know all the controllers are like that. When you turn off the power and when you start again, it should go by default to a one particular location. It doesn't need to be always zeros, but in this case it's 0. The stack. What is a stack? It's an 8 by 13 bit stack. The reason 13 bits means is the program counter is a 13 bit in length and it needs to store the counter. Okay, let's have a look at here. How does it work? Just look at very carefully here. Here's the main program. Start from here. There. Here main program starts and your computer is reading, accessing the main program. And when it comes to this address, O2E0, that address, you are calling a subroutine. Subroutine is here at that position, 100. So you are telling the computer, run to 1000 hexadecimal. So the program counter has to now execute the subroutine. Right? So a program counter has to leave this place and come and execute. When it's finished this one, it has to go back. So what it needs to do, it needs to store this address, this one, into the stack. It's there. It stores that in the stack before it executes that. That's your step 1. And you will see step 2. When it finished the subroutine, it goes back to the stack, take the value, put it in the program counter so that the main program continues. So that's your stack. You can have 8 level of stack. That means 8 subroutines you can call in the main program. If you do more than that, it just goes back to the first one. So otherwise the computer does not know where to return to. The return address it doesn't know. It was working this and then you call a routine, it came there and it doesn't know how to go back. So stack helps them. So the hardware is built such that when it sees this instruction, it just takes the current address, put them in the stack, go and finish the subroutine, and then finish it and come back, go to the stack, take the address back in and then continue. That's your function of the stack. The stack is structured first in, last out. So if you have the first address here, second, third, fourth, The first one will come out last because it has to take that one next and that, and then the last one. Now we have looked at the program counter and the stack. Now we look at data memory. Remember in the diagram, the block diagram, the data memory is here. And what does the data memory consist? There are 368 locations altogether. 368 locations, 8-bit memories. Program counter is different, right? This is 8-bit. Data is 8-bit. So the data memory is divided into 4 banks. It has got bank 0, bank 1, bank 2, bank 3. They are registers, bank of registers, and they have special functions. So if you go to data memory and you got, that is one bank, another bank, another bank, another bank. And within that, and you will find there are general purpose register. So these GPR registers are inside this bank. Then they have got SFR, a special function register. They are also in that bank. Which bank you want to use, you have to select. You must select which bank you are going to access. Otherwise, the computer does not know. Select means you need to put in some bits somewhere, and computer knows that you are going to address this bank, or that bank, or that bank, or that bank. We will come back to that. But remember the data memory, they are contiguous, but they are in a block form. Bank 0, bank 1, bank 2, and you are going to tell the computer which bank you are going to use. It's important. So you've got to program it. In the program, you're going to set it up. Again, once you do the lab, you will see that easily. Any unimplemented data memory locations read as 0. So if you don't use some of them, and if the reserved ones will have zeros in it. I thought I'd just show you the banks now. You might wonder what are these banks. So look at bank 0, bank 1, bank 2, bank 3 is inside the microcontroller, is 8-bit data. This is only a data memory. We only use them to store information. And you can look at it. First one is going from 0 to FF, which we call the bank 0. And you can see each location has got something related. So you can see PCL mean program counter, the lower byte is stored there. So similarly, informations are stored. They have got a particular name to it. So you cannot use these ones, override these ones. You cannot. You can use these ones. These registers, they are empty room where you can put data, you can take data, you can put them in. Now you decide, well, I can't do everything on bank 0. Let me go to bank 1. So you select bank 1. By selecting the bank 1, you have access to all these. And you have access to port A, and you have access to Touche. So you got to select Touche before you access port A. So you got to switch between bank 0 and bank 1 when you are writing the program. Right? But when you write it, it's just one single code you have to write. Very easy. And then I go to the next bank. That's this one, bank 2 and bank 3. This data sheet is given to you. And these are pre-assigned locations. You don't change them. There are locations you can just put values in it, which will come back to that. Here's empty for you to use. You can use these registers. And here also you can see there's register. This you can write something in it. You can write here. You can write here. So there are 3 banks. So the special function registers, first 32 locations can be classified into 2 categories. So first 32 locations are this color, that one, this color, that one for bank, and you can see I mark them as color. They're not all of them are 32. They are reserved. And they say this first few bytes in bold of every data memory bank are identical. So if you take, what they're saying is that, let's take starters. Will be there, starters will be there, starters is here, and starters is there. Because it's a very important register. There are 8 bits there. They have 1 bit is for representing overflow, 1 bit is saying your calculation is 0. So when you are in this bank, you want to access that immediately. When you are in this bank, also you need to access that. When you are in this bank, also you need to access. When you are in this bank, you need to access. If you only have starters here, then when you are in this bank, how do you access the starters? If starters are not here, if it's only here, then you're going to switch again, access it, then switch back. To avoid that, the designers have put starters everywhere, because you will find starters register has to be accessed regularly in the program. So that's what this says. Then you see peripheral registers. You want to write something to a port, reads from a port, you go and look at the port address here, 05, and write the value there in port A. Internally you put 8 bits in there, that will be available outside world. So that's what they are. Each bit of these registers is wired to the microcontroller peripherals, enabling the microcontroller to interface to the external world. So if I decided I want my port number, port C, 8th bit should be 1. All the others should be 0. I'll go to this particular location, locate my port C, that's port C. I put in a value here, I write the value as 10000000. Then I'll have 8th bit 1. And when I look at the microchip, I look at the port 8, the 7th pin, not 7th pin, the 7th position of the port C. And you will find, or you can say 8th position there. If you start from S1, if you start from S7, and that will be 1, all the others will be 0. So that's how you do. So internal registers are wired to the external world in this microcontroller. That's how you do the controlling. So we'll do more about this later on, and you don't need to remember, have this slide when you're writing in the program. Now remember that we talked about this starters register. We mentioned many times this is a very important register. We talked about it, right? So that particular starters register is what we're going to now look and say, why is that important? Why this fella in bank 0 and that fellow in bank 1, that fellow in bank 2 and bank 3, very important. So I just analyzed that bits only. And that particular starters register also tells you where you are here or here or there or there. So let's go to that particular slide, next slide. So how do you address the data memory? Data memory has got 4 banks. How do you address it? So it's known that the larger the memory, we need more bits for the address bus. So one way to avoid is to have banks and switch them, right? Is to divide the memory into number of blocks equal size, and they can be accessed with a small number of bits. Okay. So it has got 4 bank, 8-bit RAM address it has got. So how do I do which bank I know? So you go to the status register, you can pick up O3, and in the status register, if you turn off the power, automatically these 2 values will be 0, 0. That means your bank 0 is already selected. Bank 0 is when you turn on and off the power, and start again, you will find these 2 bits are automatically by default set to 0. That means you have selected bank 0. And now you decide I want to go to bank 1. I don't want to be in bank 0, I need to be in bank 1. That's where my data, I want to fetch it. So in that case, you go and there's an instruction in the computer which will show you, put this value here, that's 0, and change that to 1. In that case, you will be located, have access to bank 1. And by changing these 2 bits, you put 2, 1, and you go to bank 3. So you can program, these 2 bits can be programmed by the microprocessor instruction to select which bank you want. So default setting is bank 0. So that's a little bit knowledge you have on starters register. The starters register will have a bit 0 and bit 7. I'll explain to you all of these in a minute into the next slide. Okay, for the moment you need to only concentrate these 2 bits of the state status register, STATU status register, and it has got 4 combinations, and to select the banks. Now, with more detail inside, and again, you don't need to remember this table, you will be given. I am now in bank 0. Somehow I have selected bank 0, and that's my status register. So if I want to be in bank 0, my status register, this value, if you look at it, will be 0, that value should be 0. Then only I will be in bank 0. And you can see every one of them have got a meaning. So if you go to port A, you've got in the microcontroller chip, you look for RA7 is the pin for port A, bit 7, RA6, RA5, RA4. So if you write values in here in the microcontroller, so if I put a value 0, 0, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, this value will be available on the pins. That's how microcontroller control. This is an input-output port, port A, port B. They're connected to the external world. And then, there are other functions there. We learn all these functions as we go along, and you suddenly find so easy to use this table. They look difficult now, but once you've written one program, oh yeah, it's lookup table. You don't need to really read through a lot of things. Yeah. That's the way I'll be teaching. You don't want to go through every line of it. Similarly, data memory bank 1. You need to have this table when you're writing the program. You don't remember anything, you just have this table. Next one. Then you go data memory bank 2. Again, you need to have this table. The last bank, bank 3. Bank 3 has got these particular addresses. You need to have this table to do the job. Every bits in one particular location corresponds to something. Now we just finish this particular chapter with status register. Remember, that's an important register. Status register contains arithmetic status of the arithmetic logic unit, reset status, and bank selection of data memory. These are the main things. So what are they? And if you look at in this particular register, bit 7 is IRP. We'll come back to that. If you say read writable and is 0, means it will be always 0 you need to put in. You don't put 1 in there. But you can put initially, when I say that always 0, you can put 1 as well. But the thing is that by default it will be 0, it will be 0, 0. So readable, writable bit, it will be 1, 1. It could be anything, anything. X means anything in there when you start the system. After microcontrollers reset, you can see bracket means zeros. This is what after resetting. That you need to know that. But you don't remember, you have it, okay? So we got bit 6. I have already explained this one before to you. By putting 0, 0 in there, it will access bank 0. We look at this bit in a minute, and we look at this one. This one is 0. If you do a arithmetic calculation, and if your results is 0, you will see that bit will be 1. And similarly, other one, carry as well. We'll come back to the next page, shows you all of these. This is the next page, same status register. Now we started with the first bit, IRP. What is IRP? Bit select register bank. So it is an indirect addressing mode, which you haven't learned yet. And if you want to address a particular location, banks 2 and 3 are active, you need to go to that location. And if you put 0 in here, then bank 0 and bank 1 are active, and the memory locations are that. So which memories it makes active. And then TO, timeout. There are timer inside, and when you have set up a timer, after power up instruction, this will be 1. After watchdog timer output, it will be 0. Again, we'll program this timer, and by noticing this 1 or 0, we'll know what's happening actually. PD bar. PD bar is what you have here, which is called power down bit. So if it has got two conditions, 1 and 0, and which again we can use them after power up or after executing clear WDT instruction, which resets the watchdog timer. So if you want to reset the timer, you put in 1 there. Next one is that 0 bit. If your result of the arithmetic logical operation is 0, if this operation is 0, there will be a 1 in that particular column. And if you see 1 there, that means your arithmetic results have given a 0 output. Right. This is for carry, digit carry bit, and this one is the actual carry bit. So I mean, we'll go through them. I don't want to go every line up. This is in between carry, because fourth low order bit to the next one. So when there's a carry, when it's at the carry, 4-bit and a 4-bit, when there's a carry forward, you can actually monitor that particular bit to see whether there's a carry going in. Okay? This is carry bit. So after you've done the addition, a carry out from the most significant bit. So if you've got 8-bit, there's a carry going to the 9th one, and it will be 1. That means there's a carry is going to the 9th one. If that is 0, if this becomes 0 after the calculation, that means there's no carry going to the 9th bit. So these are positions that we need to locate them and check them. And again, in the next instruction, next chapter, but I'm just giving an introduction to how important this status register, which is available in all banks, and that you need to use them when you do the programming. So we've now come to the last, part of that chapter. So what I thought is I just put in some exercise and some questions where you can just go through all these questions and try to understand. If you are able to answer these questions, that means that you have understood the chapter on this. Purely asking you, how do you select, what does this mean, what does special register mean, and that means you go back and look. So what you're getting out of this particular chapter is the block schematic understanding of a microcontroller first, then its memory, data memory, how it is set up, and then how do you select the memory. The important register for the microcontroller is called the status register, and what the status register has got 8 bits, what are the function of that. You may not remember everything now, it doesn't matter. As you go along and write program, you will understand. But it's important to use this chapter, the data sheet I've given here, for when you're writing the programs. Again, I have used these 2 books to get some information, and some are on the web, and you are welcome to look at them as well. Okay, thank you.